Welcome to this problem walkthrough. In this session, we'll be tackling LeetCode problem number 649, titled Dota2 Senate. This is an intriguing problem that combines concepts of simulation and queue manipulation. We'll explore the problem requirements, step through the approaches, and analyze their complexities. Let's dive in. In this problem, we're diving into the world of Dota 2, where the Radiant and Dire factions are locked in a strategic battle within the Dota 2 Senate. Each senator in the Senate belongs to one of these two factions. Every senator has two key abilities they can use during their turn. First, they can ban one senator from the opposing faction, effectively preventing that senator from taking any further actions. Second, if all senators from the opposing faction have been banned, a senator can announce victory for their faction. The Senate is represented as a string, where each character corresponds to a senator. The letter R represents a Radiant senator, and D represents a Dire senator. The game progresses in rounds, where the senators act in the order they appear in the string. Once a senator is banned, they are removed from subsequent rounds. The challenge is to determine which faction will eventually declare victory through this process. The input to this problem is a single string, Senate, which has a length ranging from 1 to 10,000. This string consists solely of the characters R and D, representing the two factions. The output is a single string that indicates the winning faction, either Radiant or Dire. For example, consider a simple scenario where the input string is Senate equals RD. In this case, the Radiant senator at index 0 bans the Dire senator at index 1 during the first round. Since the Dire senator is banned, they cannot take any actions, and the Radiant faction wins. The output for this example would be Radiant. Now let's examine another example where the input is Senate equals RDD. In this scenario, the Radiant senator at index 0 starts by banning the Dire senator at index 1. Then, the Dire senator at index 1 uses their turn to ban the Radiant senator at index 0. Finally, the Dire senator at index 2 has no Radiant senators left to ban, as the Radiant senator has already been removed. Since all Radiant senators are banned, the Dire faction wins. The output in this case would be Dire. In a slightly more complex example, consider the input Senate equals RRDDD. During the first round, the Radiant senator at index 0 bans the Dire senator at index 2, and the Radiant senator at index 1 bans the Dire senator at index 3. The Dire senator at index 4 then bans the Radiant senator at index 0. In the second round, the remaining Radiant senator at index 1 bans the Dire senator at index 4. At this point, all Radiant senators are banned, leaving the Dire faction victorious. The output for this example is Dire. Finally, let's look at some edge cases. If the input string contains only one senator, for example Senate equals R, the single senator's faction automatically wins, and the output would be Radiant. Similarly, if all senators belong to one faction, such as Senate equals RRRR, that faction will win since there are no opposing senators to challenge them. For alternating patterns like Senate equals RDRDRD, the outcome depends on the order of bans. Each senator bans the next senator in the opposing faction until only one faction remains. Key observations here are that the banning process removes senators from future rounds, and the order of senators plays a crucial role in the outcome. Using a queue-based approach to simulate the banning process can help efficiently solve this problem. The first approach we can consider is the brute force method, which directly simulates the process of banning senators step by step. The intuition here is simple: start with the given string of senators and iterate over them repeatedly. Each senator takes turns banning one member of the opposing faction. To achieve this, we use a queue to maintain the order of senators, ensuring we process them in the sequence they appear. As we traverse the queue, a Radiant senator bans a Dire senator, or vice versa, and this continues until all remaining senators belong to just one faction. However, this approach comes with significant trade-offs. While it's conceptually straightforward, the repeated scanning and banning operations make it inefficient for larger inputs. The time complexity in the worst case is O(n squared, as every banning operation requires scanning the queue. Space complexity is O(n) to store the queue. So, while it's a good starting point, this method doesn't scale well for larger problems. A more efficient solution is the optimized approach using two queues, which applies a greedy strategy. Here, the key idea is to pre-process the input and use two separate queues to track the positions of radiant and dire senators. The competition is order-dependent, meaning the senator with the smaller index gets to ban the other. To implement this, we first initialize two queues, one for radiant senators and one for dire senators, storing their respective indices. Then, we process both queues by comparing the senators at the front. The senator with the smaller index bans the opponent and re-enters their own queue with an updated index, which accounts for the circular nature of the competition. This process is repeated until one of the queues is empty, and the remaining queue determines the winning faction. This approach is far more efficient, as it avoids unnecessary operations and directly focuses on the essential comparisons. Let's analyze the complexity of the optimized approach. The time complexity is O(n), because each senator is processed exactly once. Once banned, a senator is removed from the queue, ensuring no redundant work. The space complexity is also O(n), as we use two queues to store the indices of the senators. This efficiency makes the method suitable for handling large inputs. Compared to the brute force approach, this method eliminates redundant operations and focuses only on the most critical comparisons. There's also an alternative approach using a simplified two-pointer simulation. Here, instead of explicitly using queues, we use counters to track the number of active radiant and dire senators. By traversing the string repeatedly and marking banned senators, we update the counts and terminate when one faction's count reaches 0. While this method simplifies the implementation, it retains the inefficiencies of the brute force approach, with a time complexity of O(n²) and constant space usage. The simplified two-pointer simulation method has its advantages in terms of ease of implementation, but it struggles with the same inefficiencies as the brute force approach. Ultimately, the chosen strategy for this problem is the optimized approach that uses two queues. This strategy stands out for several reasons. First, it achieves O(n) time complexity, making it the most efficient option for handling large inputs. Second, it directly leverages the problem structure, specifically the order dependence and circular nature of the competition. By efficiently managing indices and avoiding redundant processing, it aligns well with a greedy approach. The use of queues to track and update the state of each faction ensures that the solution is not only efficient but also intuitive to implement. This makes it the most practical choice for solving the problem effectively. While the optimized approach with two queues introduces slightly more complexity compared to the brute force method, the performance benefits are substantial and justify the added effort. The linear time complexity is a significant improvement, especially for larger inputs, and the space complexity of O(n) is manageable within this context. The use of two queues provides a clear and structured way to handle the competition process without redundant operations. Overall, this approach strikes an excellent balance between simplicity, efficiency, and scalability, making it the ideal solution for this problem. By focusing on the indices and maintaining the circular competition structure, it ensures both accuracy and performance, solidifying its position as the best strategy to adopt. This problem revolves around a simulation of a decision-making process between two factions of senators, radiant, represented by R, and dire, represented by D. Each senator gets a turn to ban a senator from the opposing faction, and this continues in a circular manner until only one faction remains. The task is to determine which faction ultimately wins. The input to the problem is a string where each character represents a senator's faction, like RDDRRD. To simulate the process, we use two queues, one for each faction. These queues store the indices of the senators in the input string, enabling us to process their turns in the order they appear. For example, given RDDRRD, the indices for radiant are stored in Q_R as 0, 3, 4, and for dire, they are stored in Q_D as 1, 2, 5. Queues are particularly well suited here because their first-in first-out behavior mimics the circular turn-taking required by the problem. The simulation begins by repeatedly processing the indices in the two queues. In each iteration, we retrieve the first senator from each queue, or from Q_R and D from Q_D. We then compare their indices to determine which senator acts first. If R is less than D, it means the radiant senator bans the dire senator. To ensure the radiant senator can participate in the next round, we add their updated index, R+N, back to Q_R, where n is the total number of senators. Similarly, if d is less than r, the dire senator bans the radiant senator, and their updated index, d plus n, is added back to q_d. The banned senator is effectively removed from the process because they are not re-added to their queue. This decision-making loop continues until one of the queues becomes empty. At that point, the faction with remaining senators is declared the winner. If q_r is empty, the dire faction wins. Conversely, if q_d is empty, the radiant faction wins. The final result is either radiant or dire, depending on which faction prevails. The circular nature of the problem is elegantly managed by adding the total number of senators, n, to the index of the winning senator. This ensures that their turn is effectively deferred to the next round, maintaining the circular order of the simulation. Regarding computational efficiency, each senator gets exactly one opportunity to act per round, and once banned, they are removed from the process. This results in a time complexity of O(n), where n is the number of senators. Similarly, the space complexity is also O(n), because the two queues store the indices of all senators. These queues are the primary data structures used, and their operations enqueue and dequeue are highly efficient, each running in O(1) time. Indexing into the input string is another critical component, as it allows us to directly access the senators and simulate the banning process seamlessly. Certain edge cases are worth considering in this problem. For example, if all senators belong to the same faction, like RRRR or DDDD, the winner is immediately clear, as there is no opposition. Another scenario involves alternating patterns, such as RDRDRD, where the algorithm must handle the circular turn-taking and banning process correctly. Even in such cases, the queues and their operations ensure the simulation proceeds as expected. Additionally, an empty input string is a potential edge case. Although it is not explicitly stated in the problem, the implementation should handle this gracefully, perhaps by returning an error or a default value. To illustrate how the algorithm works, consider the input RDDRRD. In the initialization step, the indices are placed into their respective queues. q_r contains 0, 3, 4, and q_d contains 1, 2, 5. In the first round of the simulation, we compare the first indices from each queue, r equals 0 and d equals 1. Since r less than d, the radiant senator at index 0 bans the dire senator at index 1. The radiant senator's updated index, 0 plus 6 equals 6, is added back to q_r. After this round, the queues are updated as follows: q_r equals 3, 4, 6, and q_d equals 2, 5. In the second round, we compare the next indices, r equals 3 from q_r and d equals 2 from q_d. This time, since d less than r, the dire senator at index 2 bans the radiant senator at index 3. The dire senator's updated index, 2 plus 6 equals 8, is added back to q_d. The queues are now updated to q_r equals 4, 6, and q_d equals 5, 8. This process continues, with each round eliminating one senator from the opposing faction, until one of the queues becomes empty. In this example, after several rounds, q_r is emptied first, leaving only dire senators. Thus, the winner is faction D, and the output is dire. This stepwise simulation demonstrates how the algorithm efficiently handles the circular banning process and determines the winning faction. Here, we begin by importing the D class from the collections module, which will help us efficiently manage queues for both radiant and dire senators. Inside the solution class, we define the method predictPartyVictory, which takes the input senate, a string of characters representing the sequence of senators. We then initialize two separate queues, radiant_q and dire_q, to keep track of the indices of radiant senators, represented by R, and dire senators, represented by D. Next, we iterate over the input string using the enumerate function. For each senator, if their party is radiant, we append their index to the radiant_q, otherwise, we append it to the dire_q. Now, we enter a while loop that continues as long as both queues are not empty. This is where the simulation of the banning process takes place. At each step, we remove the front indices from both queues using the popLeft method, which gives us the current radiant and dire senators competing to ban each other. the senator with the smaller index gets to ban the other and stays in the game. To ensure fairness, we append this winning senator's updated index, which is their current index plus the length of the Senate string, back to their respective queue. This simulates the circular nature of the Senate, as senators rejoin the queue at the end of the rotation. Finally, once one of the queues becomes empty, we determine the winning party. If the radiant queue still contains senators, it means the radiant party has won, so we return radiant. Otherwise, if the dire queue still has remaining senators, the dire party is victorious, and we return dire. This simple yet efficient approach ensures that all senators get their turn in the circular order, and the party that manages to ban all members of the opposing party first emerges as the winner. Here, we start by importing the necessary Java utilities and defining our solution class with the predict_party_victory method. The method takes a string senate as input, which represents the sequence of senators from the radiant and dire parties. We initialize two queues, radiant queue and dire queue. These queues will keep track of the indices of the radiant and dire senators, respectively. Next, we populate these queues by iterating through the Senate string. If the character at the current index is R, we add that index to the radiant queue. Otherwise, if it's D, we add the index to the dire queue. This setup ensures that we know the initial positions of all senators from both parties. After filling the queues, we simulate the banning process using a while loop. The loop continues as long as both queues are not empty. In each iteration, we retrieve the indices of the front senators from both queues. These indices represent the current senators who will compete to ban the opposition. The senator with the smaller index gets the chance to ban the other. To simulate this, we add the winning senator's index back to their respective queue, but with an offset equal to the length of the Senate string. This ensures that the winning senator gets a turn in the next round after all remaining senators have had their current turns. Once the while loop exits, we know that one of the queues has become empty, which means all senators from that party have been banned. To determine the winning party, we simply check which queue is not empty. If the radiant queue is empty, it means the dire party has won, so we return dire. Otherwise, if the dire queue is empty, the radiant party is victorious, and we return radiant. This completes the implementation, where the queues and the simulation logic allow us to accurately predict the winning party based on the given rules and the initial arrangement of senators. To solve the problem, we start by analyzing the input string RDD. We initialize two queues, one for the radiant party and another for the dire party. The radiant queue contains the index of the first R, which is 0, and the dire queue contains the indices of the two Ds, which are 1 and 2. In the first round of banning, we consider the first senator from each queue. The radiant senator at index 0 and the dire senator at index 1 are dequeued. Since the radiant senator's index is smaller, it bans the dire senator at index 1. The radiant senator is then re-enqueued with a new index, which is its current index plus the length of the input string, resulting in an updated radiant queue containing 3. The dire queue now only has the senator at index 2. In the next step, we begin the second round of banning. This time, the radiant senator at index 3 and the dire senator at index 2 are dequeued. Since the dire senator's index is smaller, it bans the radiant senator at index 3. The dire senator is then re-enqueued with a new index of 5, calculated as its current index plus the length of the string. Now, the radiant queue is empty, and the dire queue contains just the senator at index 5. Since there are no radiant senators left, the dire party is declared the winner, and the output is dire. Now let's consider the input RRDDD. First, we initialize the queues. The radiant queue contains the indices of the two R's, which are 0 and 1, and the dire queue contains the indices of the three D's, which are 2, 3, and 4. For the first round of banning, the radiant senator at index 0 and the dire senator at index 2 are dequeued. Since the radiant senator's index is smaller, it bans the dire senator at index 2. The banned dire senator is removed, and the radiant senator is re-enqueued with a new index of 5. The updated radiant queue now contains 1 and 5, while the dire queue is updated to contain 3 and 4. Next, we proceed to the second round of banning. The radiant senator at index 1 and the dire senator at index 3 are dequeued. Again, the radiant senator has a smaller index, so it bans the dire senator at index 3. The radiant senator is re-enqueued with a new index of 6, resulting in an updated radiant queue containing 5 and 6. The dire queue is now left with just the senator at index 4. In the third round, the radiant senator at index 5 and the dire senator at index 4 are dequeued. This time, the dire senator's index is smaller, so it bans the radiant senator at index 5. The dire senator is re-enqueued with a new index of 7. The radiant queue now contains 6, and the dire queue contains 7. In the fourth round of banning, the radiant senator at index 6 and the dire senator at index 7 are dequeued. Since the radiant senator's index is smaller, it bans the dire senator at index 7. The radiant senator is re-enqueued with a new index of 9. The radiant queue now contains 9, while the dire queue is empty. With no dire senators remaining, the radiant party is declared the winner, and the output is radiant. For the input RRRDDD, we initialize the queues as follows. The radiant queue contains the indices of the 3 Rs, which are 0, 1, and 2, while the dire queue contains the indices of the 3 Ds, which are 3, 4, and 5. In the first round of banning, the radiant senator at index 0 and the dire senator at index 3 are dequeued. Since the radiant senator's index is smaller, it bans the dire senator at index 3. The radiant senator is re-enqueued with a new index of 6, resulting in an updated radiant queue of 1, 2, and 6. The dire queue now contains 4 and 5. In the second round, the radiant senator at index 1 and the dire senator at index 4 are dequeued. Again, the radiant senator has a smaller index, so it bans the dire senator at index 4. The radiant senator is re-enqueued with a new index of 7. The radiant queue is updated to 2, 6, and 7, while the dire queue now contains just the senator at index 5. In the third round, the radiant senator at index 2 and the dire senator at index 5 are dequeued. The radiant senator bans the dire senator, as its index is smaller. The radiant senator is re-enqueued with a new index of 8. The radiant queue now contains 6, 7, and 8, while the dire queue is empty. With no dire senators left, the radiant party wins again, and the output is radiant. In this problem, we use a queue-based approach to simulate the banning process between the radiant and dire senators. To analyze the time complexity, we start with the initialization of the queues. Here, we iterate through the input string senat, which contains n characters representing the senators. For each senator, we append their index into one of two queues, depending on whether they belong to the radiant or dire faction. Since appending to a deque is an O(1) operation, and we do this for all n senators, the total time for initialization is O(n). Next, we simulate the banning process. During this phase, we repeatedly process one senator from each queue until one of the queues becomes empty. In each iteration, we remove the first senator from both queues, compare their indices to see who bans the other, and append the winner back to their respective queue with an updated index. Each of these operations, removal, comparison, and appending, is constant time, or O(1). The number of iterations in this while loop is proportional to the number of bans that occur. In the worst case, every senator bans one opponent, which means the loop runs n times. This makes the time complexity of the simulation phase also O(n). When we combine the time complexities of the initialization and simulation steps, we get a total of O(n) for initialization plus O(n) for simulation, which simplifies to an overall time complexity of O(n). Now, let's analyze the space complexity. For the queues, we use two separate deques to store the indices of radiant and dire senators. In the worst case, each queue could hold up to all n indices, meaning the space required for the queues is O(n). Apart from these queues, the algorithm uses a small amount of additional space for variables such as radiant_index and dire_index, which are constant in size. Since no other auxiliary data structures are used, the additional space is O(1). Therefore, the dominant factor in the space complexity is the storage for the queues, resulting in an overall space complexity of O(n). Let's compare this optimized queue-based solution to a more naive approach. The naive method would involve simulating the process by iterating over the senate string, banning senators in place, and repeatedly traversing the string until one party wins. This causes the time complexity to shoot up to O(n²), because each band requires a full traversal of the string to update it. In contrast, the optimized approach avoids this repeated traversal by using queues to directly store the indices of senators. By efficiently managing the banding process through these queues, we reduce the time complexity to O(n). This is a significant improvement, as the optimized solution scales linearly with input size, making it much more suitable for large inputs. Now, let's break down the best, average, and worst-case scenarios for the optimized solution. In the best case, the winning party is determined quickly after just a few rounds, and the number of bands is much smaller than n. However, since the initialization step still requires traversing the entire Senate string, the time complexity remains O(n). In the average case, the banding process proceeds for a number of rounds proportional to n, which leads to a time complexity of O(n). In the worst case, every senator is involved in exactly one band, requiring n iterations of the loop. Even here, the time complexity remains linear at O(n). To understand this mathematically, the initialization step involves a single traversal of the Senate string, making it linear. The banding process is also linear because each senator participates in exactly one band, ensuring the total number of iterations does not exceed n. Combining these factors, the overall time complexity is O(n). Similarly, the space complexity is determined by the storage of indices in the queues, which is also linear at O(n). One of the most common mistakes when solving problems is not accounting for edge cases. For instance, if you're working with arrays, you might overlook scenarios where the array is empty or contains only a single element. These edge cases can easily lead to incorrect solutions if they aren't explicitly tested. Another frequent issue is relying on brute force approaches without considering their time complexity. While brute force can sometimes give you the correct answer, it often results in a time limit exceeded error for larger inputs. Always analyze the complexity before committing to such solutions, and think about potential optimizations. Incorrect index handling is another common pitfall. For example, using a loop like for I in range, len, array, but mistakenly indexing array, I+1, without checking if I+1 is within bounds can lead to runtime errors. Finally, modifying input during iteration, such as deleting elements from a list while iterating through it, can cause unexpected behavior. A safer approach is to work with a copy of the input or track changes separately to avoid runtime issues. Adding unnecessary complexity to your solution is another mistake to watch out for. Overcomplicated code is not only harder to debug but also less efficient. To avoid this, break the problem into smaller, more manageable subproblems and simplify your logic wherever possible. When it comes to interviews, take the time to thoroughly understand the problem and clarify any constraints before diving into the code. Misinterpreting the question is a common yet avoidable mistake. Additionally, communicate your thought process clearly as you work through the solution. Even if your initial approach isn't correct, demonstrating how you think can earn you partial credit. A good strategy is to start with a simple brute force solution and then refine it iteratively, focusing on optimizations. Lastly, always test your solution on small, custom examples to verify its correctness and ensure you've accounted for edge cases. Many problems share similarities with others, so recognizing patterns is a valuable skill. For example, LeetCode 121, Best Time to Buy and Sell Stock, is a great way to practice optimization techniques for arrays. Problems like LeetCode 20, Valid Parentheses, highlight stack-based approaches, while LeetCode 239, Sliding Window Maximum, introduces efficient sliding window techniques. LeetCode 56, Merge Intervals, demonstrates how sorting and interval-based logic can simplify complex problems. To solve problems effectively, it's important to identify common patterns early, such as sliding windows, stacks, or dynamic programming. Balancing trade-offs between time and space complexity is another key skill. Prioritize time efficiency for large inputs when needed. Additionally, practice solving problems using both recursion and iteration, as understanding when and how to use these approaches can be crucial. Techniques like divide and conquer, memoization, and pre-processing are also powerful tools for reducing problem complexity and should be part of your problem-solving toolkit. Alternative approaches can often provide elegant solutions depending on the problem type. Greedy algorithms are particularly useful for optimization problems where making local decisions leads to a global solution. However, it's important to note that greedy methods don't always work in every scenario. Dynamic programming is another powerful technique, especially for problems with overlapping subproblems. Though it may require additional space, it guarantees correctness when applied correctly. For problems with ordered or monotonic properties, binary search on answers can significantly reduce complexity, transforming an O(n) approach into O log n. Lastly, the two-pointer technique is a simple yet effective method for solving array-related problems. It's particularly useful for scenarios involving subarray sums or identifying pairs that meet specific criteria. This approach is both intuitive and efficient, making it a go-to strategy for many coding challenges. Great work! To wrap up, we covered the Dota2 Senate problem by simulating turns using a queue. We reviewed its complexities and the importance of tracking states in simulation problems. Thank you for watching, and don't forget to check out more solutions. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!